This movie is the first of two dealing with equilibrium calculations. Attached with this should be a Word document which shows you the questions I'm going to solve so we don't have to constantly keep writing them. So please make sure you have that file first, and we're going to proceed now. Let me introduce you capital Q. Q is the equilibrium quotient. And as you should know from math, quotient means it's the result from a division. And you can think of it as K, or the expression for K, but not under equilibrium conditions. Mathematically, the best thing to do is use initial values. The question then is, well, what's the purpose of Q? Well, we're going to compare it with values of K. Under this circumstance, the value K would be given at a certain temperature. You'd calculate Q for a particular set of reactant concentrations and product concentrations, and this would mathematically tell you where the equilibrium expression was, but under non-equilibrium conditions. When the value of K is smaller than Q, the reaction will shift to the left. When K equals Q, the reaction does not shift. Why? It's at equilibrium. When K is larger than Q, the reaction shifts to the right. I'm going to go on to the next page. You need to make sure you have that question. That's the first one from that handout in front of you so you can see what we're talking about. Moving on now. So we have a question dealing with sulfur trioxide and nitrogen monoxide, and we're going to write the reaction and make sure when you do this that you leave about 3 centimeters, 2 centimeters at least on the left-hand side for the headings for our ice chart. So our reaction is going to have SO3 gas plus NO gas in equilibrium with SO2 gas and NO2 gas. The coefficients are all ones in this situation. I guarantee that will not always be the case, but we're going to start here. Our initial from the question is in moles, so I recommend recording it in moles. The SO3 value is 0.400, and I always record all the significant figures in this first line so that when I'm done a question I go back and I can check to see how many significant figures I need. The NO also is 0.400. The sulfur dioxide is 0.500, as is the NO2. That's the given amounts from the question. The next thing I want to do is I want to convert this into initial in moles per liter, and that means I'm going to divide by the volume, which in the question is 2 liters. That makes the division pretty easy, and so each of these numbers divided by 2 will give me 0.2, 0.2, 0.25, and 0.25. Remember, I'm going to go back to that top line to check my significant figures so I can move faster now that I'm not recording all the significant figures. So the initial comes from the question, the change comes from the reaction. Well, I don't know which way this is going to shift yet. I don't know where my pluses go, where my minuses go. So I'm going to complete my ice chart because part of the question says work out the equilibrium concentrations. And what I find works best is if I leave a couple of lines underneath. So I'm going to leave that much space. Now I'm going to work out Q. And to do Q, I'm going to use these values here. So Q, my equilibrium quotient, as a formula equals the concentration of SO2 gas, first order, concentration of NO2 gas, also first order, divided by the concentration of SO3 gas, first order, and concentration of NO gas. Again, first order, none of these are at equilibrium, so there's no subscript E's after any concentration. At this point, I use my initial concentrations. So the SO2 is 0.25. The NO2 is 0.25. The SO3 is 0.2, as is the NO. I use my calculator, and when I round this to the correct number of significant figures, I'm going to get 1.56. That's bad. 1.56. Now is when we make our comparison. The value of K given in the question, K equals 0.500. Therefore, K is less than Q. And if K is less than Q, therefore, shift to left. So there's a reason why I put K first and Q second. First of all, that's alphabetical, and I can remember alphabetical. And the other thing is that the inequality gives me the direction of the shift. It's pointing to the direction I want for the shift. Now that I know that it's a shift to the left, I can now go back to my ice chart, and I can say, all right, if it's shifting to the left, I will have a positive value on my reactants and a negative value on my products. After that, the coefficients are all ones. That comes down from my reaction, and our variable will be X. The equilibrium line always comes from the ice chart, so it's going to be 0.2 plus X, 0.2 plus X, 0.25 minus X, and 0.25 minus X. There's obviously a limitation on the value of X, because you can't have X bigger than 0.25, because if it was, then the concentrations of the products would drop below 0, and you can't have negative concentrations. I'm going to need some space to work on the math for this next one. So I'm going to set up the equation here, and we're going to work down the page, and then when I have to, I'll move to the next slide. K equals, it's exactly the same formula as what you see on the left, concentration of SO2 gas. This time it's at equilibrium, first order, times the concentration of NO2 gas at equilibrium, first order, divided by concentration of SO3 gas at equilibrium, first order, times concentration of NO gas at equilibrium, first order. So the difference between the two is K is at equilibrium and Q is not. This time, I don't have equilibrium concentrations. I don't have single numbers like I did with Q. I have expressions from the equilibrium line. So it's these expressions from the equilibrium line that I'm going to be using in here. So we make our substitutions. 0.5, and I know the full value is 0.500, but I can short form it for now, equals concentration of 0.25 minus x times the concentration of 0.25 minus x divided by 0.2 plus x and 0.2 plus x. Once I've made this substitution, I'm now going to have to decide which mathematical process I intend to use to solve this. The rest of this lesson and the entire next lesson address how we make those decisions and how we work them through. The goal, of course, is to solve for x, and that's not the easiest of formulas, and I'm going to work us onto the next page then so we can get there, and then we'll come back as we hopefully need to. All right, so continuing from that point, we should have 0.5 equals, and I'm going to simplify the right-hand side into 0.25 minus x squared over 0.2 plus x squared, because both the numerator and the denominator were square terms. This methodology is called the perfect square. It only happens when you have any value by itself on the left, but both the numerator and the denominator are perfect squares. The entire numerator and the entire denominator are perfect squares, so there can't be anything extra attached to it. When that's the case, the most common first step is to then take the square root of everything on the left and everything on the right. What happens when we do that? Well, the left-hand side stays as the root of 0.5. The right side simplifies to 0.25 minus x over 0.2 plus x. Much friendlier equation than what we had before, but we're still solving for x. What should we do next? Well, let's address that denominator. So we're going to multiply both sides by the denominator, and if we do that, we get the root of 0.5 times 0.2 plus x equals 0.25 minus x. We still want to get x by itself, so we're going to have to expand the left-hand side. Well, the expansion is going to require me to distribute to both terms. So putting the terms in the correct order, we get 0.2 times the root of 0.5 plus root of 0.5 plus, times x equals 0.25 minus x. We now have four terms, two with x's, two with not. Collect like terms. Given the values we have here, it's easier if we move the x's to the left and the numbers to the right, because the sign on the right-hand side of the x is negative. So I'm going to have x plus the square root of 0.5 times x equal to 0.25 minus 0.2 times the root of 0.5. We're now going to factor the left-hand side. We're going to remove the common factor x, and we get 1 plus the root of 0.5 equal to 0.25 minus 0.2 times the root of 0.5. We can now divide both sides. By the 1 plus the root of 0.5. And that leaves us with this expression that says x equals 0.25 minus 0.2 times the square root of 0.5 all over 1 plus the square root of 0.5. At this point, it's going to take you some time to put that into your calculator. Make sure you have the brackets so that you can separate your numerator from your denominator properly because of order of operations. If you do it all correctly, you're going to get the value of 0.0636. Now, because of the limitations of this software package, it's hard for me to go back a slide. So what I'm going to have to do is over here on the right hand side, I'm just going to address where we go from here. We're going to go back to the expressions, and we see that the concentration of SO3 gas at equilibrium, which is exactly the same as the concentration of the NO gas at equilibrium, had the expression 0.2 plus x. You'll be able to do this directly on your piece of paper if you left the spots above. So now we have 0.2 plus 0.0636, and that's going to round it to the correct significant figures, 0.264. You've already got the heading of moles per liter in your heading, so we should be good there. As for the concentration of SO2 gas at equilibrium, that's the same as concentration of the NO2 gas at equilibrium. Its expression was 0.25 minus x, which is 0.25 minus 0.636, which will give us, to the correct number of significant figures, 0.186 mole per liter. And again, you've got the heading of those in your chart. That's the process. This looks like a fairly complicated process to solve all of this. If you think you have a faster, more efficient way, feel free. Just understand that it has to be right. Doesn't matter how fast you get to the wrong answer. Thanks for watching. We'll deal with the other two methods. Remember, this one's the perfect square. We'll deal with the other two methods in the next movie. Thanks for watching.